Our next discussion is a comparative study between recursive methods versus iterative methods. In other words, which method is preferable over the other method? You know that recursion is an alternative form of a program control. It is essentially repetition without a loop. So when you use loops, you specify a loop body. The repetition of the loop body is controlled by the loop control structure. In recursion, however, the method itself is called repeatedly, and a selection inside the method body must be used to control whether to call the method recursively or not. By comparing the two methods, we can say that recursion has substantial overhead. Each time the program calls a method, the system must allocate memory for all of the method's local variables and parameters. This can consume considerable memory and requires extra time to manage the memory. But the good news is that any problem that can be solved recursively can be also solved non-recursively with iterations. So recursion has some negative aspects. It uses up too much time and too much memory. In this case, why then we should use it? In some cases, using recursion enable us to specify a clear and simple solution for some problems that can be solved naturally in a recursive form. The decision whether to use recursion or iteration should be based on the nature of the problem as well as based on your understanding of the problem you are trying to solve. The rule of thumb is to use whichever approach that can develop an algorithm that is more efficient in terms of speed and space. If an iterative solution is obvious, then use it, and it will generally be more efficient than the recursive option. In order to show that recursive methods not always develop efficient algorithms, we are going to write iterative and recursive methods for the Fibonacci sequence and compare their performances. A Fibonacci sequence is a sequence in which each value in the sequence is the sum of the previous two values. The first two values are 1, so the next one will be the sum of the previous two values, so it is 2. The next one is a 3, which is the sum of the previous two values, 1 plus 2, and so on. So here is a sample of the first Fibonacci numbers. If we label these numbers with indices, so with index 0 we have 1, with index 1 we have 1, with index 2 we have 2. So we would like to write a method that if it is given the index, it gives the Fibonacci number at that index. And this is specifically what we want to do. We want to write two methods that return the Fibonacci value at any index given as an input parameter. The first is iterative and the second is recursive. After implementing and writing the two methods, we are going to compare their performances and state which one performs better than the other one. In order to write a recursive method for the Fibonacci sequence, first we need to define the method and then see how this method calls itself recursively. Let Fibonacci n be the value of the Fibonacci value at index n. If Fibonacci n gives us the value of the Fibonacci at n, then how we can express it in terms of the previous two values? First, we have to specify the base case. For the base case, for the first two values, they must be equal to 1. So we say that Fibonacci 0 is equal to Fibonacci 1 is equal to 1. And now for the recursive definition, we say that for every Fibonacci number, it's equal to the addition or sum of the previous two values. So we say Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2, but this will occur only if n is greater than or equal to 2. So for the base case, if n is equal to 0 or n is equal to 1, then we return 1. Otherwise, the method is going to call itself recursively by saying return Fibonacci n minus 1 plus Fibonacci n minus 2. According to that, as you see that the natural approach to find the Fibonacci number is best be expressed recursively. However, as you will see later, that the implementation of this approach is not so efficient, and the performance becomes very slow for large values of n. Here is the method implementation using iterative method for finding the Fibonacci number if its index in the sequence is given as an input parameter. In the beginning, the method is testing for the two initial values. So if n is less than or equal to 1, it is going to return 1. And these are the two initial values. Both of them are equal to 1. If n is greater than 1, then iteratively, the method is going to compute all Fibonacci numbers starting from index 2 until we reach the Fibonacci number that is at index n. In every iteration, it adds the two previous values as the Fibonacci number. To keep a track of the previous two values for every Fibonacci number in every iteration in the loop, we need two variables. One that represents the first previous value and the second represents the second value. For the first previous value, it is called first and it is initialized to 1. And for the second previous value, it is called second and also initialized to 1. They are both initialized to 1 because inside the loop, we are going to compute the first Fibonacci number, which is at index 2. And to find this Fibonacci number, we need to add the two previous values, which are equal to 1. In every iteration, we need to do three things. The first thing is that we compute the Fibonacci number from the previous two values by adding first and second and save it into Fibonacci. And this is the situation we have, that the value for the Fibonacci number is equal to 2. The second thing that we should do is that we should move the value of second into first. An order here is important. We need to update the value of first before updating the second, because the value of second will be the value of first, and the value of the current Fibonacci number will be equal to second. So therefore, the value of first will be equal to second. And the third thing that we should do is that we move the value for the Fibonacci number into second, and second will be equal to Fibonacci. So this is now the situation we have before we go for the next Fibonacci number. Now for the next Fibonacci number, it is going to be equal to first plus second. And the value of first is equal to 1, and the value of second is equal to 2. So therefore, the value for the Fibonacci number is going to be equal to 3. And we will keep doing that iteratively until we reach the Fibonacci number that is at index n, and this value will be the return value for the Fibonacci number. Here is the implementation for the recursive method for finding the Fibonacci number at index n. As you can see that the code inside the method is so elegant and simple compared to the iterative method. The method is first testing for the base condition or the stopping condition. So if n is less than or equal to 1, it's going to return 1 representing one of these previous two values. Otherwise, it's going to have two recursive calls. One will be called on the first previous value n minus 1, and the second call will be on the previous second number, which is equal to n minus 2. And the return values for these two calls will be added together as the return value for the recursive method. So we have two recursive calls in this method. Therefore, if we want to trace this method recursively, then the tracing will form a tree. Since the code inside the recursive method is shorter than the code inside the iterative method, you might think for the first impression that it is more efficient. But that is not true, because for the iterative method, every Fibonacci number is computed only once. So for large value of n, then the algorithm will not be affected dramatically. But for the recursive method, since it is calling itself twice, once on the first previous value and the other on the second previous value, then for some Fibonacci numbers, they are going to be computed more than once. And this adds unnecessary computation overhead and will make the method so slow for large values of n. As an example, if we want to compute the Fibonacci number at index 5, then the method is going to call itself for computing the Fibonacci number at index 4 and index 3. And for computing the Fibonacci number at index 4, the method is going to compute the Fibonacci number at 3 and 2. So therefore, the method is going to compute the Fibonacci number at 3 twice. Let us elaborate more about that by an example. For our example, we would like to find the Fibonacci number at index 5 using the recursive method. So when we call the method with input parameter 5, then it's going to call itself recursively first on input 4 and then with input 3. So first it is going to call itself recursively on input 4. And on input 4, it's going to call itself recursively on input 3 and 2. And when it calls itself on input 2, it's going to call itself on 1 and 0. Now these 1 and 0 forms the stopping condition or the base case. So therefore, we are going to return by 1 for both of these calls. So 1 plus 1 is going to be equal to 2. So the return value from these two calls is equal to 2. Now at this level, we have called the method with input 2. Now it's time to call the method again with input 1. So when we call the method with input 1, this is the stopping condition and the base case. So 1 is returned as a return value. So 1 plus 2 is equal to 3. So the return value from this call is equal to 3. Now for this call, we have returned from calling the method with input 3. Now it's time to call the method with input 2. And this is call number 7 recursively. And again, the input is 1. So this is the base case. So 1 is returned. And for input 0, this is the base case. Also, we are going to have 1 as return value. So 1 plus 1 is equal to 2. For these two calls, the return value is 3 and the return value is 2. So we are going to add these two return values, and the return value from this call is equal to 5. When we call the method with input parameter 5, now we have returned back by calling the method recursively on input 4. Now we need to call the method on input 3. For input 3, first we are going to call the method with input 2 and then with input 1. And now for input 2, we are going to call the method recursively on input 1 and 0. And these two calls are the base cases. So both will return 1 as a return value. When we add these two, it's going to be equal to 2. Now for this call, we have finished from calling the method with input 2. Now it's going to be called with input 1, and this is the base case. So 1 will be returned as a return value. So 1 plus 2 is 3, and 3 is the return value from this call. And finally, we have returned from calling the method with input 3. And now we add 5 and 3, and the final value is equal to 8. After enumerating all the recursive calls for this example, notice that for some Fibonacci numbers, they are computed more than once. For example, computing the Fibonacci number at index 3. It is computed more than once. The first time is computed when we call the method with input 5, and the second time it is computed when we call the method with input 4. So the computation is repeated, and this adds a computation overhead. Not only that, for other Fibonacci numbers, for example, to compute Fibonacci number at index 2, it is computed first here, and also it is computed here, and also it is computed here, so it is computed 3 times. This example is only for finding the Fibonacci number at index 5, and we have this amount of repeated computations. Imagine the performance for finding the Fibonacci number at index that is very large. Then of course there will be a lot of repeated computations and the algorithm will be very slow. Let us go to JGrasp and try to see how the algorithm will perform for large input. To compare the performance between the iterative method and the recursive method for computing the Fibonacci numbers for large input, we are going to define them on long integer. So let us first define the iterative method. So it is private static long, and the name will be fib_i, which is short for Fibonacci iterative, and the input will be, the input parameter also will be long. If n is less than or equal to 1, then we are going to return 1. Else we are going to define 3 variables: long, first equal to 1, second equal to 1, and finally for the Fibonacci number we are going to initialize it to 0 so that the compiler does not complain that it was not initialized. Then we are going to have a for loop that will start from 2, I less than or equal to n, I plus a plus, and in every iteration we are going to compute the value for the Fibonacci number, which is equal to first plus second, and first is equal to second, and second is equal to the current Fibonacci number. After exiting from the for loop, we return the value that is saved into Fibonacci number. This completes the implementation for the iterative method. Now for the recursive method, it is also private, static, long, but we are going to call it fibr, which is short for Fibonacci recursive, long n, and the implementation inside we test for the base case f n less than or equal to 1, then return 1, else return recursively Fibonacci recursive n minus 1 plus Fibonacci recursive n minus 2. To test the performance of these two methods, we are going to use inside, we are going to call the two methods within the main method. So system.out.println, and here we will say iterative Fibonacci, and we are going to call it with input 5 is equal to, and we will call it with input 5. Similarly, for the recursive method, we are going to copy this line and we are going to change the output, and we will say recursive, and we will call the method fib recursively. So now we finished the implementation. Let us save it, Control S. Let us test it that it does not have any errors. And now we are going to run it and see the result. As you can see that the output is very fast for both of them. Now let us increase the input for both of them. Let's make this one 8 as an example, and this is 8. So we need to change the input parameter 8, and this is 8. So run the program again. Again, it is fast for small input. Let me put here 50. And let us call the two methods with 50 as input parameter. Let us run the program now again. And now as you can see, for the iterative method, it is showing the result, but for the recursive method, it is still computing. So it is still calling itself, and we are waiting for the result to come out. Finally, the result is displayed after taking 42 seconds, and this is only for input 50. Imagine if you try to increase the input, let's say to 100 or 1000. Of course, the performance of the algorithm will be slow, and it is not reliable to depend on the recursive method.